Hello, everyone, and welcome to Live Academy, the virtual design learning platform by Yale Middle East Architecture Lab. My name is Riyad Jokka. I'm joining from Dubai, and I'll be moderating today's public lecture. Starting semester 3 of Live Academy, we are having a public lecture by Andrew Kudless, joining us from Houston, Texas. Andrew is the founder of Matsys and professor at the University of Houston. This session is recorded and will be broadcasted on YouTube live. Please subscribe to our YouTube channel where we will post the recording from this lecture so you can refer back to it in the future. And we will be posting it alongside other great lectures from the past and our upcoming roster from this semester at Live Academy. Our aim is to spread the work of the speakers and to have a visual reference online to their amazing body of work so you can access it at any time. If you haven't already, please also take a look at Live Academy website, which has been updated with the new roster for semester 3. We have 8 exciting technical classes at an advanced level this time in various software on generative design. This semester we also have 3 more upcoming lectures that you can join. Free of charge. Q&A will be taken throughout the session. If you have a question, please feel free to type it in the Q&A box, and I will be moderating the Q&A post Andrew's presentation. We also have some links for you here that the host has published in the chat that you can refer to for Live Academy TV, where you can get recordings of the live sessions. So please make sure to look at the links that the host has posted in the chat. Andrew's work has been on my radar for a number of years now. As one of the most successful graduates of the MTech, Emergent Technologies and Design program at the AA, I really looked up to what he was doing before I joined the program myself. And I'm very excited for today's lecture, especially that I've known Andrew for a long time. I had the opportunity of working with him in 2012 on Shellstar, amazing project, a small pavilion in Hong Kong, where it's still one of the examples that you can refer to for thin shell constructions. So it was a super rewarding project to work on back then. Andrew Kudless is a designer based in Houston, Texas, where he is the Bill Kendall Memorial Endowed Professor at the University of Houston's Hines College of Architecture and Design, as well as the Director of the Advanced Media Technology Lab. Previously, Andrew has taught at the California College of Arts, the Ohio State University, the Architectural Association, and Yale University. In 2004, he founded Matsys, a design studio exploring emergent relationships between architecture, engineering, biology, and computation. The work of Matsys has been exhibited internationally and is in the permanent collections of the San Francisco Museum of Modern Art, the Centre Pompidou in Paris, and the FRAC Centre in Orleans in France. His work on Confluence Park has won several awards, including the 2019 AIA National Honor Award. In 2019, he became the first American designer to contribute to Louis Vuitton's Objet Nomads collection. He holds a Master of Arts in the Emergent Technologies and Design program at the Architectural Association, the AA, and a Master of Architecture from Tulane University. I'm very excited for Andrew's public lecture today on Live Academy and to get started with this new semester. So please join me in welcoming Andrew Kudless from Matsys and the University of Houston.
Hi, everyone. Good morning, good afternoon, good evening, wherever you might be in the world. I hope you and your families are all healthy in this difficult time. Yeah, thank you, Riyad, for that introduction, and thank you for inviting me to the Live Academy lecture series. It's really nice to be here and to reconnect with you after many years. It's really interesting to see what you have been doing with Meal, but also the emergence of Live Academy. It seems like a great resource for everyone around the world. So my lecture is divided into kind of 4 chapters, and that kind of document some of my work over the last 15 years. So for each of these topics, I'm going to try to trace a disciplinary concern through my teaching and my professional practice. and try to trace how my ideas have changed over time, often due to kind of collaborations with people like Riyadh, or conversations I've had with my colleagues or students. So I'm going to start with drawing in the age of automation. So I never would have predicted that I'd have anything to say about drawing. 25 years ago, when I was first starting my first architecture degree, it was actually my lack of drawing skills that pushed me towards computation. That compared to my peers, they were all able to, draw fantastically well with a pencil or pen, and I was incredibly sloppy, and my drawings were always like wrinkled and smudged, and no matter how hard I tried to draw cleanly and beautifully, it was always just kind of, I felt like a disaster. And at the time, there were like 3 computers in the basement of the architecture building that I was in, and I saw like maybe like a way through computation that I could kind of catch up with my peers, that I could have like cleaner drawings and things like that. And it was interesting to kind of go through that process early in my education, and now be kind of returning to drawing over the last few years as a way to think about how I teach parametric tools, but also how I can think through different computational ideas within my own work. So before we kind of get into my work in this, I want to kind of give a little bit, maybe 4 or 5 slides on kind of the background of drawing and architecture, and work towards its kind of computational repercussions. So the relationship between drawing and architecture is foundational yet paradoxical. As the critic Robin Evans suggests, architecture could be defined by the struggle between the inherently 2-dimensional plane of the drawing and the 3-dimensional reality of space. That architects must fold the complexities of construction, materiality, and perspectival view into flat drawings, while at the same time unfolding the abstract rationality of the drawing back into built form. So for hundreds of years, the way that we worked was primarily through the parallel space of projective drawing, plans, sections, and axonometrics. And that tension that Evans is talking about was the primary tension of our work, that we had to that drawings allowed a certain abstraction that allowed us to deal with kind of higher level ideas within a project, but at the same time we had to kind of collapse all of the complexities of architecture, of view, perception, materiality, light, all of that into kind of the 2D drawing as we were working. So with the advent of CAD software in the last few decades of the 20th century, I'd say the fundamental act of drawing was relatively unchanged despite the new and different tool set. So basically, like, using AutoCAD didn't really add anything. It made drawings more, efficient, that you didn't have to like redraw a drawing when you made a mistake. You didn't have to erase things in the same way. But it didn't really change, I think, the fundamental thinking behind drawing. But only as digital modeling and more recently building information modeling have become the dominant methods used to design architecture, has architects' relationship with drawing radically changed. So after centuries of drawings being the essential mechanism to generate and critically engage architecture, we're at a moment where drawings might exist only as an output of production, if even that. Within a model-based design paradigm, the construction of drawings has either been bypassed altogether or been uncritically outsourced to algorithms. So what I mean by that is, maybe we still have to produce drawings. Let's say within a Revit model, we need to produce drawings. But the drawings are being produced by an algorithm that we're not really critically engaging. And you could say that drawings might be viewed as an anachronistic byproduct of the current legal requirements for building permits, in that potentially the fabricator or the contractor might not need drawings, but often government bodies for getting building permits still require drawings. So it seems odd in a way that if we're not, as architects, we're not really using drawings in the design process, potentially the contractor and the fabricators might not be using drawings within their process, and that the drawings, instead of being kind of the core kind of abstract generative process of the architect, they've now almost become like simply a legal contract or a legal requirement of the project. So in this void, what is the agency of drawing within the discipline? In other words, why do we draw, or should we draw? Freed from the complex historical relationships between drawing and building described by Evans, should we simply create buildings without drawings, as many have suggested? Or might the very technologies that have enabled this freedom be re-examined for their potential to critically engage drawing as a generative and creative act? So before we get into kind of how the profession might re-engage drawing in relation to computation and automation, I think it's necessary to kind of back up a little bit and talk about the ways that different academic institutions have engaged drawing through the prevailing pedagogies of computational design. So if we work through these, I think it's precisely the frustration that I have with these pedagogies that have led to several of the projects, which I'll show in a few moments. So I see 4 primary ways in which computational design is taught in universities today. So the first one in the upper left that is often referred to as design to production. So in this case, computational tools are taught as a means towards an end, focusing on real-world fabrication, typically involving digital fabrication tools or robotics. So here, drawings are seen as redundant or antithetical to progress. That is, that previously we designed something, we turned it into drawings, and the fabrication shop then took those shop drawings, or they redrew the drawings into shop drawings. They were then approved by the architect, and then the product was fabricated. So with design to production, the idea is that all of the production data is embedded within the design model or outputs of that model, like G-code and things like that. So in some ways, like the drawing is unnecessary or redundant in that process. Method 2, in the upper right, simulation and optimization. In this case, computational tools are taught in order to either simulate or optimize a particular process related to structural, energy, or other analysis topics. In this case, drawings are simply a static representation of a more dynamic process. In method 3, building information modeling. In this case, computational tools are taught as part of a philosophy I like to refer to as one model to rule them all, whereby all drawings and data are generated through a central model-based platform. Here, the drawing process is an afterthought required by the legal permitting process. The idea being that you have to model everything possible, and that model controls everything, and then the output is simply the drawings, and it's not really, let's say, a part of the process. And then method 4, case studies and parametricism. In this case, computational tools are taught in relation to the stylistic tropes that have unfortunately become synonymous with the tools. Many students don't know the difference between computational design and parametricism. Here, drawings, if used at all, are again simply representations of a more idealized dynamic model. In effect, none of these pedagogical methods really engage in drawing as a generative act. They either reject drawing, minimize its importance, or treat it as a product. Is there a way of teaching computational design that facilitates the ability to generate, or ability of drawings to be generative? And furthermore, looking forward into the profession, the need for drawings is rapidly being subsumed by new technologies. To give just a few examples, TestFit.io is developing model-based tools that make early feasibility studies parametric. In a recent conversation with TestFit's CEO, Clifton Harness, their goal is to automate 80% of the tasks of architects currently performed through laborious drawings. Upcodes is developing software that could one day eliminate drawing-based permitting sets through real-time and automated model-based code checks. Their goal is to fast-track permitting processes by bypassing both physical and digital drawings as the primary evaluation media. So the idea there, and they actually just won a major case up in the US Supreme Court related to who owns the the codes, basically. And what Upcodes has been doing is basically they have digitized the codes of various jurisdictions within the United States. And the idea is that they could then turn those codes, those written codes, the legal codes of how steep a staircase could be or how long a hallway could be before an exit and so forth. And they could parametricize those into a plugin for various different software packages, and that you could simply test your model against the actual code. And if your model doesn't pass the test, it would then give you suggestions on where it's failing the test. And if it does pass the test, it would automatically pass the city's permitting process. So again, that the model is the thing being checked, not the drawings. Moving on, in the lower left, Fologram is developing augmented reality-based tools that could one day eliminate a contractor's need for drawings. Rather than contractors referring to either a digital or physical drawings, they will be able to virtually see the building's model on site. And then finally, game engine-based rendering platforms like Lumion or Twinmotion, which through their speed and realism have become the go-to tools for communicating with clients over far more abstract drawings. So again, why do we draw, or why should we draw? And how might drawing be productive in the age of automation? So Kelly Baer, one of the contributors to the first volume of the Drawing Code Show, which I co-curated in 2017 with Adam Marcus, has discussed how drawing, rigorously and intensely pursued, maintains a sense of surprise and innovative discovery. So quote, "The drawing becomes a catapult for invention, leaving behind the expectations of convention, buildability, or financial burdens. Drawing is a proto-document of proto-document of something that is not quite finished, an act still underway in the eye of the author." In this respect, drawing might capture the abstract logic of an idea better than any other form of media. About 9 years ago, I changed my teaching methods for computational design from one based on famous case studies in contemporary architecture to one based on case studies from mid-20th century art and computation. This was based on a conversation that I had with a student who, when I suggested that he should use Grasshopper to complete a part of his project, he told me, "Oh, I never learned Grasshopper because I don't like twisting towers." At that moment, I realized that my computational design pedagogy had failed to convey the rich capabilities of the tool, and many students simply thought that the tools were only important if one was interested in parametricism as a style. That is, for me, I was actually managing or coordinating the curriculum, and I knew that all of the students that I was having had already gone through a series of classes on digital modeling, computational design, and so forth. So to have a student say, "Oh, I never learned those tools because I wasn't interested in a particular style," was like, although I was sad for that student, I also realized it was actually my fault that I had not conveyed the importance in the proper way, in that I thought that if I taught it through, and if other faculty members had taught, like, "Oh, here's this cool twisting tower," they would all see the value of the tools based on that specific case study. And many students were simply turned off by the tools because of the relationship with certain types of architecture. So that shift in thinking, for me, it was like, although I saw the value of the tools, it was hard, I think, for students who weren't as knowledgeable about the larger kind of world of architecture. And for me, it would be like someone saying, "Oh, I don't use keyboards because I don't like writing novels." It's like, well, you can write a lot of different things besides novels with keyboards. But that it's as if you only saw people using a computer keyboard to write a novel and you didn't like reading fiction, then you would be like saying, "Oh, I'm not going to use a keyboard anymore. I'm going to handwrite everything from now on." Like, for me, it didn't make any logical sense, but I totally understood the perspective that students had for that. So I think there's a critical difference between the inherent value of a tool and how one particular group has used that tool. So using minimal and abstract art as case studies allowed me to introduce and discuss essential math, logic, and geometry topics to students without having to wade through how some of these techniques have been applied during the period that the architectural historian and theorist Mario Carpo has referred to as the first digital turn. So in my own professional work, I have also explored the generative capacity of computational tools, or computational drawing, I should say, to explore ideas. I think some of these, I think of these as computational sketches. So if hand sketches are what you often refer to as the direct connection between the mind and the hand, computational sketches are a direct connection between the mind and the machine. These are thought experiments that are played out with computation as a partner. And for me, they're often the seeds for future projects. So in this particular sketch, it starts with a simple circle. And then I'm just kind of flipping through different iterations here, where basically the circle gets kind of broken at each, there's like a, kind of think of it as like a generation, like each generation, the circle gets, there's a random mutation, either happens or doesn't. And if it does happen, there's kind of this like bump or another circle or arc that it forms on the original circle. And then the next generation has to kind of deal with that kind of random mutation on it. And by changing the length of those random arcs, the frequency by that the mutation occurs, if it occurs only kind of in or outside the circle, you get many different kind of iterations that you can see here. Small changes in the rate of mutation, its strength or variability, and the rate of growth produce large differences over time. I return to these computational sketches again and again in a way a craftsperson might return to her toolbox. I tune the script to produce new design opportunities or to align with material or fabrication parameters. I've used this particular computational sketch over the last 3 years to make robotically drawn ink drawings, ceramic 3D printed vessels, concrete benches for a forest cemetery, and a proposal for a rug for Louis Vuitton. In the same way an architect might return to a partie diagram repeatedly to mine new opportunities, I try to mine the generative capacity of algorithms. So for that drawing codes exhibition that I mentioned with the Kelly Bear quote, in addition to curating or co-curating the exhibition, I also contributed a drawing myself. And I was developing the drawing in the tense period between the 2016 election and Trump's inauguration in early 2017. And I wanted to explore in my contribution to the exhibition how I could use computation to help generate and represent kind of a counterfactual walled city. Trump's constant ranting about the wall was chilling, disturbing, and reminded me of like a medieval warlord. Obviously, the wall is an architectural device traditionally used to divide people and territory. Trump's talk of the wall reminded me of these maps of walled cities, and I began to wonder if I could script a wall to somehow simultaneously become territory and city. So rather than dividing the city from the territory, I wanted to, like, how could the wall be simultaneously both of those things? What could a city look like if it was both, if it was wall and nothing else? I've been fascinated with walls that have grown thick enough to be buildings in themselves. So I started a computational sketch that slowly increased the wall's length while preventing it from moving outside a site or intersecting itself. At a certain point in the growth process, the wall takes over the entire site. There's still an inside and an outside to the wall, but sometimes the outside is deep inside the site boundary or vice versa. At that point, I was left with a big squiggly wall, but realized that I needed some sort of roofscape to make it read as a city and not just a thickened line. I also wanted to push myself to learn new tools. The goal was to produce a sketch that was believable enough with the help of automation to spur questions about the nature of walls and their possible use to confuse sidedness and to unite rather than divide a community. That's when I turned to Google's autocomplete feature to give me suggestions on what programs a rooftop might support. I worked my way from A to Z, pretty much accepting whatever suggestions Google autocomplete gave me when typing in the word rooftop followed by the letters A through Z. And I started designing parametric definitions that could implement that program on a number of different random sites along the wall's rooftop. So you see here, like I would type in rooftop, what was it, like I, and then I'd have these list of different words, and maybe sometimes like rooftop I didn't have anything that was kind of architectural, so then I would type rooftop IA and rooftop IB and rooftop IC, and I would just keep on iterating through the first letter and the second letter of the word until I found a list of words that were kind of architectural in some way, and then I would just choose from that. So in the end, a rooftop ice skating rink was, one, and you can see a few of those and how they kind of morph depending on the snaking of the underlying wall. Last year, Adam Marcus and I had the opportunity to experiment with these ideas further with students during a one-day workshop at the University of Miami. Using pre-built scripts provided to them, we asked students, and these students were everything from like 18-year-old, like their first week of architecture class, to graduate students in architecture. So using pre-built scripts provided to them, we asked students to develop a seed algorithm that would produce a basic block pattern. Buildings, trees, and crowds would then populate the city automatically. Students would then iterate through how the changes in the base seed pattern would result in massive changes in the whole urban pattern. Finally, we asked the students to almost work backwards like archaeologists to hypothesize on what political, cultural, geological, or economic systems might have led to their generated cities. The goal was not to become urban planners. Instead, it was to understand the biases embedded in with the base geometry of our imagined cities. All right, so that's the end of the first chapter. The next chapter of the lecture is on the material practice of architecture. So after I finished my first architecture degree, I think in 1998, I lived in Kyoto, Japan for a year. And I don't know where all of you are in your degree or if you've graduated already, but like maybe some of you, after 5 years of being an architecture student and living kind of the life of an architecture student, I wondered if architecture was actually for me. That, as many of you know, the way that architecture is taught, unfortunately, is kind of punishing for a lot of individuals, and it's almost like a military boot camp. Sometimes it feels like, and that you feel like you're being pushed to the mental and physical limits. And at the end of those 5 years, I was actually quite skeptical if I wanted that as a lifestyle or as a career choice. And while I was living in Japan, I actually had kind of decided that architecture wasn't what I wanted to do. And I decided to pursue a degree in traditional carpentry, Japanese carpentry. And I decided I would try to spend the rest of my career in Japan. Unfortunately, that didn't work out with the visa requirement, and I actually had to return home to the US. And that was kind of heartbreaking for me. And I had to kind of figure out, like, now that I'm back in the US, what do I do? And I ended up, coming back into, let's say, the fold of architecture. But I think one of the things that I learned in that process of kind of questioning architecture was that in the traditional training of an architect or of a carpenter in Japan, that the first year was solely focused on learning how to make your own tools. The idea was that until you mastered your own tools and materials, there was no point working on buildings. Yet, that you would spend the first year making these planes or chisels and learning the kind of, almost the muscle memory needed to plane a piece of wood properly, and why you would choose one plane versus another plane, or one chisel versus another, and how to repair those chisels, how to make your own depending on the type of joint that you were needing to make. So this idea of learning the tools and materials of your discipline before engaging in the production of the discipline stayed with me after I came back. I became fascinated with the diverse group of architects who seemed to have focused deeply on specific material systems, such as Eladio Dieste in Uruguay with bricks, or Paraguay, actually, I should say. Freado with fabric, Felix Candela with concrete, and Privé in France with sheet metal. Some of these practitioners embodied the historical archetype of the master builder, in that they were not only the designers of the structures, but also sometimes the general contractors. At the same time, in my teaching, I had become frustrated with the methods I was using to teach design. I realized I was simply repeating the ways that I was taught and had been focusing on site and program as the sole generators of design concepts. We are all familiar with the studio model, faculty introducing a site and program during the first weeks, followed by weeks of site and program analysis. At some point, there'd be some mysterious magical moment that a concept would develop out of that analysis, and then students would, pursue that analysis or pursue that concept, let's say, based on their analysis of site and program for the rest of the term. And so that's the way I was teaching. And the resulting projects of my students were good, but they also felt kind of divorced from the material realities of construction and the possibilities available when one starts from a specific material system as the design generator. So in 2014, the frustration was too much for me, and I decided to flip my studio teaching around such that I would ask students to choose one material or one way of making and produce 5 large egg-shaped objects over the first 4 weeks of the term. Only after they had blundered through the first couple of attempts would they begin to understand the craftsmanship required to work with the material and gain fluency with it. At that point, I would then introduce the program and the site, and then they, with their new material knowledge, would begin to apply their material system to the design problem. So the reason I did this is that I realized that I think the way that I was taught and the way that a lot of my peers were teaching was based on this model that site and program were the sole generators of concepts. And I realized that how, I think, incorrect that is. That if you look at any famous architect, that they all have their biases, that there are these often both material biases, that they tend to use certain materials, or that they tend to use certain systems of like grids or generative logics, let's say, based on material systems. And they repeat the kind of working through those material systems project after project after project. And the projects are each different. And the reason they're different is because of different sites and programs. But the reason that they're very similar is because the architect had this kind of these biases towards a certain way of working. And it was just kind of shocking to me that we only engage students in the engagement of site and program as the generator of design, rather than what I thought was a much more foundational development of a design, which was this engagement with material systems. And that the differences only come about once I think an architect has like deeply engaged those material systems and is able to understand how to tune them to different site and program parameters. So in 2015, I was asked to revamp the MArch Studio one studio. So basically the first studio that students take at the California College of the Arts. These are students who are new to architecture. They're graduate students, but maybe they had a degree in chemistry or English or whatever before. So they're older students, but they are new to architecture. And I've loved teaching the studio over the last 5 years, 6 years or so, because it basically attempts to introduce students to the material practice of architecture through hands-on experimentation. The term was divided into 7 2-week assignments that explored the relationship between material, form, and performance through full-scale assemblages and large drawings that together built what we referred to as totems. I wanted students to discover design opportunities that only come out of a deeper understanding of working with their hands, with concrete, wood, steel, and plastic or paper sheets. I wanted students to gain a deep respect for the labor of architecture and the laborers who make it possible. That is, that despite what we often think, or that we, in popular culture, that like architects build, is not really true. Like we make models and drawings and instructions to build. But obviously there's a huge amount of labor from other disciplines of craftspeople that go into the actual building of architecture. And I think often our education is so kind of divorced from the labors of producing buildings, not producing architecture, but of producing the actual building, that we often don't understand the importance of that knowledge, of often generations of laborers, and how they have been trained in a certain way of making. So having students in their very first day of class learn how to cast concrete, learn how to use a saw, learn how to use a welding torch, a laser cutter, and so forth, was really, I think, enlightening for me as a teacher, and as well for, I think, my students. So in 2018 and 19, I also introduced a eighth topic to the studio, which exists as a kind of a meta project throughout the term. So 3 years ago, while finishing up Confluence Park, which I'll talk about later, with my colleague Tina Florian at Lake Flato, I asked her what was one thing that she wished architectural graduates knew when she hired them. I was expecting some sort of answer around a technical skill, like, oh, they should know Revit, or they should know this or that. But instead, that she said that she wished architectural education better prepared architects for collaborative design. Very few projects, she said, are completed in isolation. Most require interpersonal skills that allow architects to quickly jump on or off of a project and to build towards a collective goal. As such, over the past 2 years, I've had students switch projects every 2 weeks while building these totems. Despite a lot of concerns that it would be a disaster, I was happily surprised how the projects were as good, if not better, than previous years of students working solo. Rather than each student being solely responsible for an entire project, they are essential collaborators of 7 different projects, and it can take collective pride and ownership in producing a much larger whole. So the way I kind of introduced this to students, I said, this might seem kind of crazy and difficult for you to like work on it really hard and intensively for 2 weeks, and then hand it over to someone you don't really know. Or the other way around, to jump onto a project that you know almost nothing about, and then somehow like try to like decipher the concept that the original student had developed, and then build on that concept and make it your own in some way. But in this case, to do it through a new material and a new kind of generative logic. So I think the other way I kind of maybe, let's say, convince them is that I could say, look, instead of having one project in your portfolio at the end of the semester, you can have 7 projects in your portfolio. You may have only worked on each one for 2 weeks, but your contribution was valuable. And this is much more similar to the way that it will be like when you're working in a firm. You'll be pulled off of one project and be put on another project that you've never worked on, and you'll have to quickly adapt to that new project and understand both the conceptual but also the technical. Like, how do you organize a model, the layers in a model appropriately, so you understand, so that someone new who has never seen it understands how to work with it. How do you hand off, how do you verbally describe what your concept is to someone who's never seen it, so that they can kind of understand it. And I think it was incredibly valuable, and I think it bonded students in a way that was, I think, really interesting, in a way that's different than asking students to collaboratively work together on a project simultaneously, but ask them to collaboratively work on something sequentially, and that one student takes on the product of another and then has to hand it off to another. All right, so moving on to my own practice and talking about material practice of architecture, I'll just mention 2 completed projects that have influenced my desire to put the material practice at the foreground of my design process. In 2015, I was commissioned by the champagne company Perrier-Jouët to produce an installation for their booth at Design Miami. Perrier-Jouët is one of the oldest champagne houses, and their founders amassed the largest private collection of Art Nouveau works in France. In fact, their own bottle was designed in 1902 by the glass artist Émile Gallé. I was asked by the company to reflect on their collection and produce new work inspired from it. Two of the most prominent features of the art and design movement were its commitment to breaking down the distinctions between the fine and applied arts, and its use of sinuous curves drawn from nature. These fibrous strands, often representing vines, hair, or flowers, unify a work by drawing your eye across it. I wanted to work with a series of different strands to produce the installation, but it wasn't until I visited their vineyards, winery, and caves in France and the site in Miami that I began to form a material and spatial concept. My goal was to evoke the materials and processes used within the growing, processing, and storage of the champagne within the space at Design Miami. 4 materials were chosen from their site and process, and then developed into specific furniture or design objects within the space using a fibrous or strand geometry. Each of the 4 projects attempts to capture the organic flowing geometry of the Art Nouveau period, while also using contemporary tools and fabrication techniques. So I'll step through each of these 4 parts of the installation, starting with the screen. So there were 3 large oak screens that create a private experience away from the chaos of the exhibition hall. So probably some of you have probably been to design fairs. Design Miami is incredible, and I encourage you to go if you ever have an opportunity. In that it's a giant tent, basically full of galleries, design galleries from around the world, showing some of the most phenomenal design from the 20th and 21st century. So, all of these chairs and tables, other design objects that you've seen in probably your history classes, that are just displayed everywhere, all around this giant tent. And there are thousands of people wandering around looking at it. But it's, as a designer, I felt overwhelmed, that there's just it's the concentration of good design is incredibly high. The density of it is incredibly high. Everywhere you look, there's just amazing design. And which is invigorating, and you feel so creative and inspired. But at the same time, it's like the number of people, the number of work is just overwhelming. And I wanted to create like a clearing, like a quiet place, a dark kind of quiet place where you could kind of escape and have a break, a way to kind of collect your thoughts and just reflect on everything that you've seen. So using the oak veneer, I explored how thin micro veneers could be cut and assembled into these glowing fibrous strands. The parts are assembled without any glue and only require the interlocking of tabs to create a strong column. Each screen was composed of roughly 75 columns that create a clearing in a forest where the visitors could rest, grab a glass of champagne in the relative peace and quiet before returning to the hubbub of the design fair. So the irony of Design Miami, like I said, is that there are hundreds of chairs, but nowhere to sit. Each of the booths exhibit some of the most iconic chairs of the last 2 centuries, but no one is allowed to sit on them. For the Perrier-Jouet booth, I wanted to create an oasis where visitors were free to relax and sit. Using the hand-carved chalk caves of the winery as inspiration, I worked with Concrete Works in Oakland, California, to create a series of 16 concrete stools that mimicked the natural beauty of the caves. Each stool was identical, but through the use of an irregular hexagonal tiling, they can be moved into larger benches. It was great seeing how visitors could come into the space and actually be shocked that they could sit down. They were, like they would just look around and look like they were nervous, like, can I really do this? Is someone going to yell at me if I sit down? And that they could kind of move these stools and rearrange them into benches or small groups, and kind of take ownership in a way that they couldn't in the rest of the fair. For the central table, I worked with my friends Ron Real and Virginia Sanfratello, who I believe will be one of the other lecturers in the Live Academy series in another couple of weeks. from emerging objects to print 7 large flutes that aggregated into a luminescent cocktail table. After being resistant to 3D printing for years, I was turned off by the black box kind of nature of the fabrication process. I learned how to program the G-code directly, which allowed me to create a woven pattern of the bioplastic strands that reference the wicker baskets used during harvest time with the grapes. As the melting strands slump from one level to the next, they create a series of truss-like structures that greatly increase the stiffness of each leg. Finally, I wanted the ice bucket to be the most closely tied object to the actual champagne making process. If you think of champagne as the liquid essence of the grape, I wanted the ice bucket to represent the solid essence of the fruit. I wondered what happened to all of the skins and seeds after the juice was squeezed from the grape, and I set out to get some of this material, as it is usually discarded or composted in the winemaking process. Luckily, I found a startup in Sonoma, California, near where I was living, that was collecting the skins and seeds, drying them, and then grounding them into a gluten-free baking flour that they had just started selling at grocery stores in San Francisco. I acquired a few buckets worth of the Chardonnay grape skin flour, and again, working with emerging objects, was able to 3D print the ice bucket components. Due to the limited size of the printer, we printed 8 interlocking parts that were then sealed to make them waterproof and then assembled into the final ice bucket. The rippled surface pattern of the bucket recalls the dried skins of the grape, like the surface of a raisin. The other project that I'll briefly mention in this chapter are the shelves that I designed for Louis Vuitton's Object Nomads collection last year. My goal was to use the expressive potential of materials and fabrication processes to evoke my feelings on travel, the focus of the collection. For me, I feel pulled in 2 directions when I travel. There's the tension between the lure of the unknown with the pull of the familiar, an inherent conflict between the joy of the new and the comfort of home. The shelf uses the strength of wood and the suppleness of leather to form a joint between the 2 materials that evokes this tension and equilibrium between being pulled in 2 directions. For the freestanding version of the shelf, I wanted to take this tension even further through producing material strangeness. The shelves appear to hang in space like the other version, but as your eyes move up, there is no apparent support. Through the use of 3D printing, we are able to produce slender aluminum branched columns that are embedded within the leather and are connected to the oak shelves through hidden joints made with a 5-axis router. The third chapter of my lecture is named after the subtitle of Tim Morton's book, Humankind: Solidarity with Non-Human People. Tim Morton is a philosopher and writer, actually based here in Houston, Texas. So I'm using it as for the name of this chapter, as it best describes a number of trajectories and desires within my teaching and practice. So I began my architectural education in the early 1990s at the transition between the postmodernist and the deconstructionalist trends within architecture. Neither movement held much influence on my education, as they both felt divorced from the real or the natural world. I felt more like clever games accessible to a select few. Instead, probably the most influential work from that time on my education was On Weathering from Mohsen Mostafavi and David Leatherbarrow, exploring the way in which water, lichen, and other organisms and processes change architecture over time. Similarly, there have been other books like 1,000 Years of Nonlinear History, Subnature by David Gisson, and Animals and Neighbors that have influenced me over the last 20 years. So I was lucky enough to share an office with David Gisson, an architectural historian and theorist, as he was writing Subnature. Its focus is on the often forgotten life outside of the LEED certified world of corporate architecture's engagement with nature, and it was enlightening to me. Similarly, DeLanda's evocation of the organization and evolution of biological, geological, and cultural entities, and O'Connor's unveiling of the non-human life that surrounds and pervades our cities and buildings, have expanded my understanding of my own role as a designer and inhabitant of the world. So urbanization and industrialization have increased the physical and conceptual distances between humans and non-humans. Our cities and landscapes have created a sort of toxic monoculture of humanity. So like in a way, a similar way to how like certain industrial farming practices where they might farm corn or wheat like over and over again on the same soil, and which requires, you know, more and more pesticides and herbicides and depletes the nutrients of the soil until the soil is kind of desolate and turns back into desert. I feel in some ways that the way that architecture has approached kind of urbanization has done something similar, and that we've created, instead of the corn or the wheat being this kind of toxic monoculture, that humanity itself is the toxic monoculture. So furthermore, the way in which contemporary architecture engages the non-human world could generally be categorized into total rejection, or basically that the non-human world, that when it inhabits our cities or our buildings, that we treat it as pests. So these are some images on the far left of bird, what do they call them? Pigeon spikes. Basically spikes that architects put on buildings to inhibit birds from landing on buildings and, you know, shitting all over them. Or this horrible example from London, where in a wealthy neighborhood in London, the neighborhood installed bird spikes on trees so that birds wouldn't land on trees because their cars were getting bird shit on that were underneath of the trees. So basically, one way that architecture has engaged non-human world is to kind of treat the non-human world as like the enemy, or as these pests that need to be eradicated. Or in the middle image, another strategy is through kind of reduction, let's say, that that there's all of this emphasis on sustainability, which is important, of course, but often sustainability reduces our engagement with the non-human world through a very intense focus on reduction of energy, of how energy efficient your building could be, but not really how it engages the natural world, anything beyond that. And of course, you know, reducing energy use does, you know, make the earth kind of a healthier place to live, let's say, but it's not it's a very indirect way of engaging the non-human world, I would say. And then finally, the images, you know, on the far right, you know, two iconic projects, beautiful projects, but at the same time, the way that they engage the world is through what I would call benevolent separation, or historically in architectural history, what we refer to as the picturesque. That we position architecture as other, you know, as something different from nature and separated from nature, and that our engagement is simply like a view from either from the architecture out into the natural world, or it is, you know, the contrast between the architecture and the natural world. So essentially, engagement through separation. So in my teaching over the last few years, I've attempted to discover or rediscover other ways of living with the non-human world. In 2018, I co-taught an advanced studio with Nathan Lynch, the chair of ceramics at the California College of the Arts. And we used this image of the 1886 Sylvester Rotting sod house in Nebraska in the United States as a studio prompt. This photograph is primarily a portrait of a rural American family and their earthen home. Yet it also captures multiple non-human species that were essential to the human family's survival. Some of these species are wild, some domestic, and some in the limbo in between, yet they form a web of connections that envelop the architecture of the home. In an age when we are finally recognizing the extent of our deep relationships with the environment around us and the microbiome within us, the studio sought a way to solve. So the philosopher and theorist Donna Haraway, paraphrasing another philosopher, Bruno Latour, states, quote, "We have never been human," end quote. When 90% of the cells of our body are non-human, it's impossible to build a wall between us and them. We co-evolve, constantly adjusting to each other and forming symbiotic or commensal relationships that are complex to unravel. So that quote, "We have never been human," I think is incredible. It's so challenging in a way because it sounds so paradoxical. Like, we're humans, of course we're humans. How can we have not been human? But it's paraphrasing Bruno Latour's quote of "We have never been modern," in that his critique, to paraphrase him, was that we have moved from, let's say, from our let's say, I don't know, religious or other kind of pre-modern beliefs of believing in kind of this magical world of that we didn't, let's say, fully understand how things worked, but we created kind of different reasons for the kind of structure of the world, and we've replaced that in some ways with a modern religion of science that we, in some ways, the general public also does not understand. And in that, so his idea is that there's a continuity between, let's say, the pre-modern and the modern, in that we still have this kind of belief systems that allow us to kind of make sense of the world, that even though we don't really understand those belief systems at the heart of them. And for Donna Haraway, paraphrasing that we've never been human, that there is a concept of what humanness is, that we understand, that this form, or your form is a human. But the more we understand who we are especially in a microbiome level, that 90% of the cells of our body are not actually human cells. They're cells of bacteria, of fungi, of viruses, of many other species, some of them harmful, but the vast majority of them are we live in symbiosis with them, and without them we would die. And that understanding of what it means to be human, I think we can follow that into what it means to produce architecture. So in my students' work, in this particular student, Maya Antonetti, her wonderful project, she explored the ecology of a specific bat species endemic to the agave plantations of Mexico, and developed a ceramic wall system that could increase the habitat opportunities for the bats, the primary pollinator of the agave plant. The bricks were designed to be hollow to allow pregnant and nursing bats the necessary warmer microclimate, while the male and other female bats occupied the cooler exterior folds of the brick. So again, going back to the material practice of architecture from the previous chapter, that the way that she was engaging kind of the design of the project was first through the design of a brick using 3D printing ceramics. And that required her to understand the toolpath of the machine, which required her to understand the G-code that was required to run the machine, the consistency of the clay, to gain kind of an inherent knowledge over like what clay, how wet the clay had to be, or how stiff the clay had to be to produce the desired overhangs and curvature that she wanted. And to understand, would it crack in the kiln or not? And all of that was going into the design of the project. And what we normally think of as architecture was, the design of a plan and section and so forth was in some ways meaningless to the project. And that it was really about the design of a detail that engaged the non-human world, and how architecture becomes a kind of facilitator of a larger ecology. So in Nick Tangi's project, he responded to the predation of a particular native species of gecko, which is also the primary pollinator on his home island of Mauritius in the Indian Ocean, by an invasive and larger species of gecko, by producing a column system that would allow for the native species to move and nest within it. And this term, in the University of Houston, Hines College of Architecture and Design, I'm teaching a studio that continues to explore these ideas within species native to the Houston region. The idea is to expand our understanding of who we design for, to include the life that surrounds us, We are living in their environment as much as they live in ours. So in my own work, I'll just briefly touch on this topic. My early exploration of non-human life primarily focused on biomimetic formal and structural systems that were inspired by natural growth patterns. Later on, I began to explore ways of fabricating components that use self-organizing systems to discover stable states. The P-Wall series of projects was originally developed as a living facade system. However, when one version was commissioned for the San Francisco Museum of Modern Art, it became an art piece hanging statically in a museum. In response to that, I produced this alternative fictional version to help me envision my understanding of the project in its intended environment. I wanted moss and lichen to grow on it. I wanted birds and insects to call it home. Although sometimes interpreted as an abstract melting of the white gallery walls, I wanted it to become much more alive and inviting to the life around it. There is a resonance that the wall has with our own bodies. People are drawn to it. It looks soft, but is rock hard. And despite that, people want to feel and hug it. The wall and our bodies share geometries because we share similar material process. But the human body is essentially a liquid interior held back by an elastic skin and held up by a compressive skeleton. The forms that emerged in the wall were the result of a similar interaction between the rigid frame, the elastic fabric, and the liquid slurry of plaster. As a designer, one of the things I learned from this series of projects was to give up control to these other forces. That is, I learned that I was a better designer when I partnered with other life and forces in the design process. I could create things that were beyond my own ability to draw or model them. We need to rethink the way that architecture has created an artificial division between humans and the richness of the world. We need to develop strategies that move beyond sustainability or the picturesque and actually invite the living and non-living world into architecture as both a design partner and neighbor. Okay, so the final chapter will focus on the integration of form, fabrication, and performance. And building on the last chapter, I see natural forms, forms built through geological or non-human agency, as a starting point to find a better integration between the geometry of a building, the way it is made, and the way it performs. If we're going to discuss the forms we find in nature, we need to talk about how these forms come into being. As architects, we are used to talking about form, but we often do so in a way that separates form from matter. About 100 years ago, the zoologist Darcy Thompson was also struggling with this disassociation in his own discipline between form and matter. At the time, a battle was raging between the Darwinists, who believed form was simply the result of natural selection, and the vitalists, who believed natural form simply appears through a mysterious vital energy. Thompson's contribution to this was to reveal how the physical forces such as gravity, surface tension, and many others led to formal patterns that we see across both the organic and inorganic world. And the title of his book is where I'm drawing the title of this chapter and lecture from. So, quote, the form then of any portion of matter, whether it be living or dead, and the changes of form which are apparent in its movements and in its growth, may in all cases alike be described as due to the action of force. In short, the form of an object is the diagram of forces. And just to be clear here, when he says whether it be living or dead, he doesn't mean a dead organic matter. It doesn't mean like a dead animal or a dead tree. He means like geology or a river or something that has never been living, that is inorganic, or like a soap bubble or anything like that, that the form of both things that are living, like a plant or a human or a protozoa or anything like that, or a rock, a mountain, a river, so forth, that they could be described in similar ways as being formed through their movement and growth. So I was immediately drawn to this way of thinking and how it has influenced a range of architects and engineers such as Gaudi, Otto, and Eisler. Form isn't something that's abstract, but a mediator of force and the result of a specific material logic. Over the last 12 years, I began experimenting with ways in which fabrication data and structural performance could be integrated into the design process rather than something we simply addressed at the end of the design process. In 2012, I taught a 4-day workshop at the University of Minnesota with Mark Swackhammer, where students developed a small pavilion made from $200 worth of cardboard. The amazing thing about this structure was that I was sure that it was going to fail. Only as the last few cardboard components were added to complete the structural flow through the thin surface did it become rigid. Later that year, I collaborated with Riyadh, the host of the lecture series today, in Hong Kong on the Shellstar Pavilion. The project was designed and fabricated over 6 weeks, and it was only possible through the tight integration of form, fabrication, and performance data within the model. So this trajectory in my work led to Confluence Park in 2014 through 2018. I'll spend the rest of the talk discussing the design and fabrication process for this project. I want to begin by recognizing my partners on this project. Tina Florian was the project manager at Lake Flato Architects, Chuck Neves was the project engineer at Architectural Engineers Collaborative, and Josh Zabel was the project lead at Chrysler Associates, who was the fabricator for the formwork. I'll focus on the design, engineering, and fabrication of this innovative tilt-up concrete structure using fiberglass composite molds. The design was produced through a small but multidisciplinary team that valued the integration of form, fabrication, and performance through the application of biomimetic principles, computational design and fabrication, and original construction logics. The BHP Pavilion is in San Antonio, Texas, and is the central outdoor classroom and community hub of Confluence Park. There were 3 primary project objectives that the pavilion needed to satisfy. The first objective was to create an educational space that could integrate the architecture of the pavilion with the client's mission to educate the community on the critical role of water in the regional ecosystem. The second objective was to create a unique and inspiring iconic pavilion to help catalyze a new identity for this historically underappreciated part of the city. The final objective was to use innovative fabrication technologies and methods to lower the overall project costs while meeting the client's ambitious educational and aesthetic vision. While most structures attempt to visually minimize the shedding of rainwater, we decided to use the pavilion to celebrate the collection of rainwater and to make the form of the pavilion a pedagogical device for the park's guides and visiting teachers. So I should say that the program, like I said, it's an educational park, but I think 14,000 students have visited over the last 2 years, I think. So basically every day, a school group, school buses show up, school kids come out, and then their teachers and the park rangers then teach students about the role of water in the Texas ecosystem. In this part of the world, there's very long dry spells, droughts, and then there are these incredible downpours that happen a few times a year where the kind of massive floods occur. So the form that emerged from this process was based on the doubly curved fronds of many local plant species that cantilever out to collect and redirect dew and rainwater back to their root stem. The double curvature not only gives these cantilevers more strength, but also the curvature creates a channel on the top surface for the efficient flow of water. Rather than design a singular large shell pushing water towards the structure's fringes, we started to design several funnel-like doubly curved forms that opened up to the sky and channeled the rain into an underground cistern where it is reused for the site's irrigation and toilets. Although the new doubly curved funnels aligned with the pedagogical mission of the client, the complexity of making these forms initially resisted easy construction strategies. Early designs for the funnels involved complex steel and cable net structures, which, even if each was identical, were beyond the modest project budget. At this point, inspired by the work of Felix Kendall and Hines and many others who had investigated the use of concrete to create complex forms that align with structural forces, the team quickly moved to concrete as the primary material. It became necessary to begin to divide the funnel shapes into discrete parts in order to break the forms into manageable sections, while also allowing views into the interior of the funnel. However, while the earlier steel funnel shapes were designed to cantilever and be supported through tension rings that could balance the forces around the entire funnel, The discrete concrete parts no longer had this tension ring and required a new solution. The design team decided on a simple solution of pairing each discrete funnel part with a symmetric paired element to create 11 structurally independent arches. The resulting arch is the simplest of structures, the statically determined three-hinged arch. An arch structure plays to concrete significant compressive strength while minimizing its limited tensile strength. Referring back to the biomimetic inspiration, each half arch was nicknamed a petal. An additional benefit to this new organization of petals or half arches was the idea of using a modified tilt-up concrete fabrication technique. Tilt-up concrete construction, famously used at the Schindler House in Los Angeles in 1921, is defined by concrete panels being cast flat on the ground on site and then lifted or tilted into place and connected to the foundation adjacent panels. The technique can be considered halfway between cast in place concrete and precast concrete, as the panels are cast on site but not on place. Thomas Edison, one of the early originators of the technique, stated the advantage as, quote, tilt-up construction eliminates the costly, cumbersome practice of erecting two wooden walls to get one concrete wall. Also, I should note here in Texas and in many other places in the United States, tilt-up concrete now, although it was used in 1921 for one of the most famous houses in the world, the Schindler House, now it's primarily used by like Walmart and Home Depot and big box stores like that, because it's one of the cheapest fabrication strategies for building very large structures. So I think it's interesting for us to have kind of used what here is deemed as like one of the lowest forms of construction, one of the cheapest and kind of dirtiest, let's say, forms of construction for Confluence Park. So in the context of Confluence Park, tilt-up had a distinct advantage over cast-in-place concrete, as it more easily allowed for reusable molds, which could be erected in one place on site throughout the construction phase. That is, we didn't have to like take the formwork down and rebuild it in the same way that a traditional concrete structure happens, that we could basically keep the formwork erected on site in one place and then continue to cast these petals again and again. Each mold we cast, I think, 10 times, or roughly about 10 times. When working with modular systems, it's difficult to escape organizing systems that reinforce the appearance of repetition. After exploring various uniform grids, an irregular pentagonal tiling grid was developed. The Cairo pentagonal tile has 4 long edges of the same length and 1 short side. When this pentagon is subdivided into 5 triangles, it results in only 3 unique triangles. Basically 2, what I'm calling A triangles, 2 B triangles, which are the mirror image of the A triangles, and then 1 C triangle, which is an equilateral triangle. When working with modular systems, the center of each pentagon represents the funnel, drain, and the edges of the pentagon represent the apex of each arch. Each A triangle is paired with its mirror B triangle from an adjacent pentagon to produce a full arch. Similarly, each C triangle is paired with a C triangle from an adjacent pentagon. In order to produce the final pavilion plan, various selections of A, B, and CC arches were explored and analyzed for the shade produced as well as the informality of the arches when seen in perspective. The design team tried different multiple options of arch arrangements to produce a pattern that was both completely modular yet appeared irregular. So what I mean by that, just to reiterate, I mean, it might seem self-evident, but like if you use a grid in your project, the appearance of the grid will be noticeable often, right? So I mean, it's very self-evident, but it's, I think, a problem in some ways. And for me, what I was trying for is like if we had arranged this in, let's say, a square grid or a triangular grid, a regular triangular grid, when it would have made everything modular, but when seen in perspective from the viewer, all of the columns would line up with each other, and you would immediately understand the regularity of the entire structure. And there would be no like surprises, let's say, in viewing it as you move around. When you view a grid, like a regular grid from any point, it kind of looks very similar from any other point in the space. Whereas if you use an irregular grid, let's say like or something that's not a grid. Let's say in a forest, I think some of the beauty of a forest comes from the irregularity of where the trunks are placed, that they don't align. And if you ever go to a tree farm where everything does align, where the trees have all been planted on an orderly grid to kind of maximize the harvesting of those trees, and either for an orchard or for their wood, there's something kind of disconcerting, I think, about those forests, because they resist kind of what we expect a forest to be, the informality of the spatial arrangement of the trunks. So I was trying to get at that informality while still using a modular system. And part of that modularity was coming up with the number of A panels, the number of B panels, the number of C panels, so that they were roughly equal. And what's not shown here, just so that we could get the same number of pulls off of each mold, that basically each mold's value was roughly the same from a cost standpoint. So what's not seen here in this drawing are 3 other smaller pavilions that are each made out of 2 pieces, or 2 petals. So there's a total of 10 of the C petals, and I believe 9 of the A petals and 9 of the B petals. So roughly equal for all of the molds. So in parallel with the selection of the specific plan arrangements, development of the sectional properties of the geometry were also being developed. For both structural reasons and water flow capture, the petals had to retain a double curvature. In order to test how water would flow on the petals, a rainwater simulation script was developed. The petal parameters were modified until the rainwater flows all ended at the drains at the base of each petal. Although a traditional wooden formwork technique was explored, similar to how Felix Kendall made many of his structures, it was determined to be far too expensive and inaccurate for the project. Instead, we worked with Chrysler and Associates to develop a fiberglass composite mold. Historically, digital fabrication has been used in some of the largest and most expensive projects, while less expensive projects used traditional techniques. However, in this case, the traditional technique was far more expensive than the digitally fabricated fiberglass molds. In addition, the fiberglass mold was not only less expensive, but it was stronger, more durable, and more accurate. The 3 formwork modules were fabricated off of 5-axis and 7-axis CNC milled EPS foam forms. After milling the forms, a 50 millimeter thick composite structure composed of inner and outer layers of fiberglass composite with a central core of balsa wood was applied. One of the biggest advantages of using this method was that the milled surface of the foam positive was highly accurate, and that all accumulation errors that are inherent to any fabrication process were always offset from this surface instead of working towards it, as would have been the case if a traditional method of cutting out ribs and laying plywood sheets over top of it had been used. Due to the size of each full petal formwork, roughly 9 meters wide by 8 meters tall, each of the modules had to be subdivided into 3 primary subsections in addition to several side forms that could be shipped to Texas. After the formwork was positioned such that it could be cast as a modified tilt-up wall construction, the rebar was added to the formwork. The fact that the bottom surface of each petal was cast against the smooth fiberglass, while the top surface was cast open to the air, allowed the 2 sides of the petal to have radically different finishes. In addition, because only one side of the concrete had formwork and the top side was open to the air, it reduced greatly the cost of all of the formwork, whereas a traditional formwork system, you have walls or formwork on both sides. In order to have the petals resonate with the flow of water, even when it was not raining, the open top side of each petal was broom finished with the direction of the broom aligning with the flow direction of the water. In the end, the 3 molds were used to cast a total of 28 concrete petals ranging from 20 to 36 metric tons each. Here you can see the construction workers broom finishing the top surface of one of the petals as it lays at a 45-degree casting angle. Petals were cast in pairs, and 2 cranes were used to lift each petal from the formwork to its final position. As you can see here, the petal is both moved in plan and rotated in section by the crane, and then attached to the foundation and to its neighboring petal. Although the structure appears as a network of connected vaults, similar to many shell structures like the Shell Star Pavilion that Riyadh and I worked on, each arch is actually structurally independent. Not only did this reduce the lateral loads being passed between arches, it also allowed for more easily fabricating the entire structure from only 3 unique molds, which reduced the construction waste. So like I was talking about with that cardboard shell structure, but also happened with the structure in Hong Kong, that they are incredibly weak until the entire structure is complete. So because you're passing loads kind of laterally through that skin, and which makes the fabrication of it very, very difficult, because you essentially need to have scaffolding everywhere in the structure until everything is in place. But by kind of in this particular project, we kind of tried to solve for allowing each arch to be statically kind of determinate structurally, that it didn't rely on any lateral forces to hold it up. It was all kind of self-sufficient, and all of the forces were resolving themselves down to the 2 column bases. And that allowed for much less construction waste. We didn't have to have as much, scaffolding to hold everything up. It allowed us to reuse the molds throughout the entire time, but it also allows the structure to kind of evolve over time, and that every structure kind of moves over time as the ground underneath of it settles. And with this project, one of the big concerns we had was when we had it more as a continuous kind of structurally interdependent structure, interdependent shell, if one foundation piece settled differently than another foundation piece, their cracks would start to form across the shell. But by having them structurally independent, number one, we reduce the number of cracks that might appear, but also that the connection detail that's at the very top of the 2 petals where they meet at the apex, where normally like a keystone would go in a traditional masonry vault, there's a hinge there, and that each foundation is structurally independent. So if one foundation kind of shifts down by a few millimeters or something like that, the hinge allows the entire structure to kind of change, and that the form basically will move without the structure itself having to, like, without the concrete having to change, or by change I mean crack, and because obviously any cracks that appear eventually let water in, which then rusts the concrete, degrades the structural capacity of the concrete over many years. So this project demonstrates that when a diverse and collaborative team focuses on the smart application of new technologies and focuses on the integration of form, fabrication, and performance, innovative projects that meet the client's mission are possible even within modest project budgets. All right, so that concludes my lecture. So thank you for your patience and for your time today. And I'd be happy to answer any questions that you might have.
Thank you so much, Andrew. That was wonderful. It was really great to see all the great work that you've been putting out from your studio, explained by yourself and your journey to get there, the process and the concepts behind the work. And I really enjoyed the section on drawing. It reminded me, I'm actually reading The Alphabet and the Algorithm by Mario Carpo, and it reminded me of a section in the book which talks about authorship. In this section, Carpo talks about Alberti's treatise on architecture and how he argued that the authorship of a building actually belongs to the builder, because architects have authorship over the drawings. And past this point of no return, where no further changes could be introduced to a project, the builder takes on the notations, basically, of architecture and makes them into a reality. So the building itself takes form past the drawing stage and becomes almost something else. How do you feel, from your standpoint, as an architect. And I hope that the audience is okay with me starting with the first question. I was so excited to ask this question and to get your opinion on it. But please post your questions in the Q&A box, and I'll get to them as soon as possible. You can also use the raise hand tool if you'd like to join the conversation with Andrew and myself and ask your question live on camera. So Andrew, how do you feel this question of authorship has changed, particularly in this day and age where architects are using those tools, where there's more seamlessness between the drawing stage and the actual physical construction of a project or the digital fabrication of the project? How do you feel this question of authorship has changed for yourself?
That's a great question. I'm trying to think of, like, there's so many different ways I could answer the question, you know, from the lens of what I was talking about with the student work and kind of like passing the work from one person to another. And that in the end, each of those projects were the result of 7 different authors. And that in a way, it was almost impossible to say who is responsible for what. Even if they were like, one person did the concrete piece and one person did the wood piece and so forth, that in the end, it was like an emerging, kind of evolving idea that all of them were kind of simultaneously responsible for. Another way that I could answer that question is in relation to, you know, the relationship between the human and non-human. And here I don't mean particularly like the organic non-human, but like more of the technological non-human, the robot or the algorithm. And that when I'm working, I'm often, you know, let's say I think I'm in control of the algorithm and I'll be producing something, and it's often like the glitches and the bugs in the algorithm, and that basically I don't understand the algorithm as well as I think I do, and the way that the algorithm performs enlightens me into other ways of working and almost teaches me a new technique, and that I see the algorithm then as, or at least maybe like my failure to understand the way that something works, like the instructions, you know, going back to your question of the architect being the writer of the instructions, that when I code something, that I'm again the writer of those instructions, but the way that those instructions are followed out by the computer is not always the way that I intended. And sometimes that's a problem, but often it's actually an opportunity. And it's almost like this conversation that then forms between me and the algorithm. And that I then, like, I'm like, what just happened? Like, why is that? Like, that's really cool. I don't know what's going on, but you know, and I have to then like dive deeper and have this like conversation with the algorithm and try to figure out how to like tease that out and understand it better. And then finally, another way I could answer the question is, you know, going back to the kind of master builder kind of model of the architect, that yes, the architect is the maker of the instructions, and the way that those instructions are interpreted, it can often be different by the builder. And let's say during like the European medieval period, when kind of the role of the architect and the builder was kind of synonymous, or in people like Kendall, who were simultaneously a general contractor and an architect, that there was that kind of, that they were both writing the instructions, interpreting the instructions, rewriting the instructions, and building it. I think it's incredibly interesting, but at the same time incredibly risky too, because you have to have a very good multidisciplinary mind, number one, a multidisciplinary team, and that the world of architecture has become so expansive that it's almost impossible for one individual to have all of those different disciplines within them and to be the author, the sole author of the whole thing. And I think it's it's like a fool's errand. And I think even in the kind of design to production model, where the designer is integrating all of the fabrication data and the all of that into their project, it still requires an enormous effort and enormous body of knowledge to inform those algorithms to make them do what they need to do. So on all of my projects, as much as I want to integrate and have kind of that master builder, kind of role, I still require a lot of collaboration and a lot of moments where I just hand off control to others, either other individuals, other companies, or like I said before, other like algorithms or other life in some form.
Mhm. It's very interesting. My other question is more on a technical standpoint, and I really enjoy those openings in the Confluence Park arches, the pedals. I was wondering, is that to drain out snow to not have any dead load or on the?
No, I mean, do you mean the holes? Yeah. No, it's kind of funny. I mean, it doesn't snow in San Antonio, or it doesn't snow, maybe once every 10 years or something it snows. So it actually came about through a project by Le Corbusier, which was finished only about 10 years ago. So when I was teaching at Ohio State, there was another professor there named Jose Oburi, who was Corb's last intern in the 1950s or so. So he was like, I don't know, 20 something years old. And he was working on this church with Corb in Firminy, France. And Corb then died, and the project went on hold and eventually on hiatus. And 50, 60 years went by. And Jose is now in his 80s. And he got the opportunity to basically finish the project based on the drawings that he had worked on, 50 years before. And in that project, I encourage you all to look it up. If you just search Firminy Corb, you'll see it. That it's a very simple church where it goes from a plan. At the base of the building, it's a square, and at the top of the building, it's a circle that's kind of on a tilt, and it kind of morphs. It's just like a simple loft, basically, between two forms. And they inserted a series of very similar, different diameter holes in. There are no windows at all in the concrete, other than the giant skylight at the top of the building. But then there are these small diameter holes that are inserted into the wall of the concrete, and it's a very, very dark space. So instead of having like a stained glass window or something like that in a traditional church, there are just these rays of light that move through the space. And as the sun moves, those like spotlights, and it's actually more complex than a spotlight. They actually milled a helical, like a screw-like pattern into these acrylic inserts. So the light hits these lenses, gets kind of twisted around with these helical grooves, and then gets splayed out as these arcs along the inside of the concrete wall. And I was just so inspired by that project. It was so beautiful. And when you look at these photographs, how these arcs of light move throughout the day, I wanted something similar at Confluence Park. That I knew obviously the light coming through the gaps, these 4-inch gaps between the different petals, that there would be these rays of light coming through there. But those rays would, because the gaps are 4 inches wide and they're so long, that the light would be very bright and continuous. And I wanted these lenses, these holes in the concrete, because each one is arrayed normal to the surface. For some of them, there's just, the light might only align with it for like 5 minutes in the entire year. And when you're there, because it's not as dark as the church at Firminy, it's actually quite hard to tell, but there are these little lights that appear almost like twinkling stars on the ground they'll just show up for 5 minutes. And because the length of the tube is, 4 to 6 inches long or 8 inches long for some of them, So the light, the angle of light it really is only just a couple of minutes that the sun is in the perfect position. So it's just like a way to create these moments of surprise in the project for the visitors. And there are a few other moments like that in the project, that some of them intentional, some of them unintentional, that I only discovered afterwards, that were there to like have this, like make the project have this life of its own outside of, like that it changes so much with the way that light moves. It changes with the way that where people are in the space, depending on the sound, radically changes acoustically. And the way, like I was saying about the forest kind of metaphor, that you think you understand the project in one way, and then you move to another place in the project and you realize that it's something different than you thought. And I wanted that grid in a way to be like this almost hidden logic that you had to really work for to understand. Like it felt very organic and informal, but at the same time, there's like this, you think there is some hidden structure there.
Yeah, no, I really enjoyed that, the description of the grid, because you can see that, the touch points of the structure do have some informality to them, which is really nice. And I really like also one aspect of the design, which is, and you explained why you did that, where the pedals are actually, it's not a continuous flow of forces. They're segmented in a way, but between them you have these really nice sort of gaps that have a very interesting lighting going through them as well. It's really nice to see that concrete is also flexible. So the stilt in place method for construction was super interesting, and the fact that these foundations might move, so you had those joints. So super interesting project. We have
just real quick, one of the I think interesting parts of that was early on in the project, the client asked us to, they were worried about the rain coming through all of the gaps.
The gaps, yeah.
Yeah, and they were like, oh, well, I think we need to, cover them with something. But we like the light coming through, but we need to cover them. So could we have like glass somehow go between them? And I was like willing to, entertain the idea, but I was also really, really worried, because I thought a bunch of mullions and all the details that you need to keep the glass, in place. And then we weren't gonna have any glass walls. So it was like, it seemed a little strange to need it. And it was one of those things that I was just really hoping would get value engineered out of the project. And it did, because it was like incredibly expensive to have all of that glass.
Expansion.
And when you start thinking about how, if you have these like two pieces of concrete and one moves slightly, and the only thing connecting them is glass, we had to make all these really complex gaskets that would allow the glass to shift in 3 directions. And it was a nightmare. And between the engineer and I, like we were just like, this doesn't make any sense to do this. It's going to cost a lot of money. Most probably the glass is going to crack over time. It's when the storms that we have here are very, very big. So if it's raining, like the rain is coming in at a 45-degree angle anyway, and you're going to get soaked. And the client had even said at one point that he was like, I want this to be the type of project that if it's raining outside, you look outside your window and be like, honey, it's raining, get the kids, let's go to the park. He's like, I know that sounds crazy. Like, why would you ever go to a park when it's raining? But he's like, that's the type of park I want. So we had to kind of remind the client at that point that we were like, look, you want this to be the type of park that people not only are going to get wet, but they're going to celebrate getting wet. They're going to celebrate this amazing climactic event that reinvigorates the landscape with water. So why put a stupid piece of glass up there? Absolutely. And the engineer likewise was saying that if we connect anything, we're going to most probably create more opportunities for the concrete to crack. Like whatever post we need to put in that would hold the glass in place, that post is going to get lateral forces, and it's going to eventually pull out of the concrete. And we're going to, and you might, the thing that gets, convinced everyone is like, that's these cracks. Like if there's any concrete falling from overhead, you're going to be liable for someone getting hit.
Absolutely.
So yeah, it was one of those perfect moments that we could just get rid of it, and it made the project so much better.
Yeah, absolutely. A piece of concrete falling on your head is a lot less enjoyable than rain. That's for I just looked up the definition of confluence, and it means a flowing together, which I think you've really captured that through your collaboration with your, with your collaborators, and also of how the project was envisioned and executed. So really well done on that. Mohammed Shamil is asking a question here. He says, thank you for the presentation. You seem to be in the sweet spot of academia and practice, whereby you have demonstrated how one has influenced the other. Building on the response of your students using Grasshopper and its associated design style, do you have similar conversations with colleagues from academia or your school where the architecture program is based? According to you, what should change in the current architectural education? And how can you bring about this change? Thank you.
Yes, definitely. Good question. In fact, I made a presentation to my colleagues at the University of Houston on Friday afternoon about this very topic. Yeah, I think it's, every school is different, so it's hard to make a general statement. But every university, every institution is going to have to deal with how do you train architects to not only know how to use the tools of today, but use the tools of tomorrow. So the way I think about it is like, what can I do to make sure that my students 10 years from now are equipped to use software that doesn't even exist right now? And so it's like a really hard question. It's like, how do you prepare them for the unknown? And I often tell students that, like, no matter what I'm teaching you, whatever software technique I'm teaching you right now, most likely in 3 or 4 years, it'll be outdated. And the most important thing for you to learn is to be adaptable and to understand some of the fundamental geometric, trigonometry, scripting, some of these things that, although they certainly will change, the fundamental principles underneath of them don't change all that much. And that we've been using like vector algebra for millennia. And that's no matter if it's structural design, parametric design, environmental, lighting, rendering, you kind of have to have understanding of like what vectors are. And so what I'm trying to do in my own teaching and the coordination of my colleagues in the curriculum stream that I coordinate is to, number one, be very flexible and constantly updating the teaching methods and the content that we teach, but also be very aware of some of the fundamentals, and not just computational fundamentals. Some of the fundamentals, like, I don't think we teach sketching enough. I think like one of the problems that I feel a lot of my students have is that they, in some, not just here, but in many other places that I've taught, that students have kind of jumped on like the digital side of things so quickly that they never really understood how to draw their ideas quickly by hand with a pencil or a pen. And I don't mean like, a mechanical drawing. I just mean like sketching really, really quickly. And because they don't have that, and at the same time, especially early students, they don't have facility yet in the digital tools, that there's like a impotency where it's like they can't do either. They have an idea in their head and they can't do it in Rhino, they can't do it in Grasshopper, they can't sketch it. And they just feel so helpless sometimes. And I feel like we definitely need to teach students to draw really well and really quickly. That I think, like, within the industrial design world, I think is the value of the drawing is actually much more, the hand drawing is valued much more as a design tool. But at the same time, I also think we need to teach students to computationally sketch. That like I was saying, that the use of the computer isn't just something that it's like a tool to get production drawings out, that it should be that you should be sketching, you should be able to sketch with code, sketch with Grasshopper, do quick sketch models in Rhino, and not feel that it has to be perfect or worked out, but that you understand the fundamentals of how to do something quickly without, in the same way that you don't worry if something is perfect when you're sketching with a pencil, that we need to get to that same point with the computer, knowing that we can then embellish that script with more and more information and refine it and add more detail to get it to the point that it can be output in whatever format we need for fabrication or legal permitting or whatever.
Absolutely, and also thinking in sort of a pseudocode kind of way. So thinking project of the steps you need to take to get that sketch out is super important. I think that wraps up our conversation for today. Thank you so much, Andrew, for joining us. I know it's early morning over there, so I hope you enjoy the rest of your day. And
thank you.
I really appreciate as much as I see the audience is appreciating your great work. I really appreciate that you shared it with us today here on Live Academy. So thanks a lot, and please stay in touch.
Yeah, thank you all, and good luck with the rest of your workshop over the next couple of weeks.